Hello again. As promised in my last video, I make another video with the laser tube here. This is a Argon laser tube from a medical laser. It has an output power of about 2.5 watts. And it needs about 10, maybe 20 kilowatts to produce this laser beam. So the efficiency is very bad. That's the reason why we have water cooling here. Well, let's have a look at the tube. So this side is the anode. This is the output windows where the beam comes out. You can see the output mirror here. Then we have some little bit of insulation around that. Here is a flexible gasket because the mirrors can be adjusted mechanically. The voltage here is about 200 volts, maybe a little bit higher for the big tube here. The burning voltage, and it also needs a starting voltage, a high voltage peak of about maybe 3 to 5 kilovolts to ignite the discharge inside the tube. Then we have here the cathode with 2 terminals here for the heater, the filament. The other 2 terminals you can see, oops, it's a little bit heavy for one hand. The other 2 terminals down here were not connected. I have no idea what they are good for. We have an electromagnetic coil here along the tube. It's a copper winding. You can see it here. It goes all along the tube. I think that's to narrow the electric discharge inside the tube to a smaller diameter. Then we have here a reservoir tube. It's just a metal tube that is connected to the filling port here. This side is soldered or welded airtight after filling. We have a water in or out, depending on which way you want the water to flow. There is of course a mirror on the other side. Looks about the same as the output mirror, but this one should be 100% reflective, while the output mirror is only partial reflective. It has to allow some parts of the beam to go through and come out of the tube. Okay, let's see what we can do with this tube here. It didn't start up inside the machine, so there was either a power supply problem, or what I suspect is this tube just has too many hours on it. Of course it could be refurbished, but well, that's not something I would like to do. I'd rather like to take it apart. Well, it's still a bit a mystery. It looks like a copper tube, or 4 copper tubes. The plastic here seems to be a little bit more than just heat shrink tube. It's like dipped into this plastic stuff. It could be a heat pipe that goes into the tube to remove some of the heat of the gas if it gets hot, but I'm absolutely not sure if that's true. Okay, the rest was some sort of heat shrink tube. It's just a, I'd say, a stainless steel tube, weld shut here on the top and the bottom. Let's have a look at the output mirror. This round face plate here is attached with 4 screws, and we have 3 screws here, which are, I assume, to adjust the angle of the mirror. So now, after removing these screws, the whole assembly is not adjusted anymore. But since this tube will not work anyway, it's not a big problem. So, can we move that? Yes. You can see that I can move the mirror, and this bellows-like thing here just allows me to do that, while it keeps everything airtight, and I think dust tight is more important in this case. I had to make myself a special tool. I only had a hex key like that, but I needed one with an angle, and that's the only one I have with non-metric sizes. I only have metric tools here, most of them, so I had no key that fitted here. You can see this half circle shaped retainers here. So this part is now loose, so I should be able to remove the rest of it. Okay, that part should come off, but somehow it's still sticking here. Oops, that was the gas filling. Okay, it's not just a seal against dust. It's also a seal for the entire laser tube. Okay, very interesting. This sealant here looks like some very soft metal. Of course, a rubber gasket here or a rubber seal wouldn't do the job. It must be something more gas tight. You can now see the mirror here. That's the exit mirror or the output mirror. And that's about the color of the laser beam. It's a blue-green color. I think it was about 500, I don't know. I will write it in the comments how many nanometers we have here. Here is some grease to make this part move a little bit easier on that part, and of course insulation, because possibly this part here is under high voltage. Let's see inside. So the gas that, well, I don't think it escaped, it's more like a low pressure inside this tube. But the gas inside would be argon, which is not toxic, at least not in these small quantities. Okay, there is not too much to see. I will try to open that screw here. Let's have a look inside. There are two copper terminals. One has the input cable attached and the other one is not used. Maybe they are both for the same anode electrode, but possibly the second one has another function. I just unscrewed the reservoir tube here. It only has two screws. Now to remove the tube, I had to unsolder this tube here, but that's something I don't want to do now. So I think I simply cut this tube here. Okay, it's just a copper tube with nothing inside. Okay, seems the tube is now loose. There's another rubber here. This rubber gasket is of course also for the water cooling, which runs inside this tube here. So here must be a seal to prevent the water coming out that way. Okay, now it's still wet. There's some greenish stuff. I think that's some copper oxide. You can see it now. There is nothing optical inside. It's just a tube. The mirrors we have already removed. That's it. Let me say a word about this white stuff here, this ceramic material the tube is made of. It's beryllium oxide, which is a absolutely wonderful material. It is light, it is very strong, it has a good electrical insulation, and it conducts heat very well from inside to the outside. But if this material breaks, or if you start to grind it or want to drill it or smash it with a hammer, you shouldn't do that, because it creates dust. Of course, everything makes dust when you hit it into pieces, but this dust is extremely toxic. So if you breathe that stuff in here, you will get almost 100% sure lung cancer. So it's better you leave it in one piece. It's not dangerous like that. It doesn't rub off in any way. But, well, maybe you shouldn't lick it up, but you should absolutely not destroy this stuff. Okay, just leave it in one piece. And if you have to dispose it, take care that it doesn't just goes to the landfill or something. So it has to be disposed properly. This is really an environmental problem if that goes somewhere. So just to repeat that, do not break it, do not grind it, do not drill it, do not smash it into pieces just to have a look inside. Don't do that. It's the same brass ring as on this end, of course. It has the same function. Okay, I think there's not more we can disassemble here, because I already said it, it's too dangerous to open that stuff. I don't want this dust in my apartment here. Okay, let's see what happens with the other parts. Funny detail here, some person with the name Course has assembled this tube on July 6th, 1991, and he measured something. It is less than 0.025. I think it's inches, maybe millimeters. I don't know what it means, but that's certainly the day when this tube was manufactured. It's amazing, but this part here is still relatively heavy. I think most of the weight is this copper coil here, which seems to be quite a bit massive. Let's see if we can remove that somehow. I think the first part would be to open the screws here. Then we can slide off this. Okay, there are also, it's not aluminium here, it's steel, maybe stainless. It has to be very rigid to support that laser correctly. So. And another one. It's certainly a nice material to build something. And that's the third one. Works without a problem, except that I'm destroying my stuff on the desk here. Okay, how does it look? Well, just a brass tube with fittings, and there is a gap between this tube and the laser tube, and the water is running through that gap. Okay, some cable ties. So I think, because there is a flange, there is also a flange, so they probably wound the entire coil with the tube or onto the tube, so I don't think we can move it away like that. Okay, I loosened that knot here with another brutal method. I just tapped here to make this part turn, and then it was loosening the knot too, and the other one was already loose for some reasons. Massive brass rings. Aluminium. Nice for reattaching the 3 rods. Maybe I can use that for something. Making a tripod of some sort. Okay, let's cut that open. I think I best will start here. A lot of expensive Captain tape. Stuff is really strong. Okay. The other side. I'm cutting right into the paper tape too. Okay, paper tape. Okay, now it turns out that that's the end of the teardown video so far, because this winding here has been soaked with some epoxy resin stuff. Can see it a little bit better here. Here is the copper with insulation, of course. Now it's some kind of rubber, like a silicone. It can be scratched away, so it's more like maybe against humidity or something like that. Yeah, well, there's the winding falling apart, so it's not impossible to remove that copper, which is quite a lot. And also the brass tube is relatively massive, so I think I have something for the copper recycling that gives a few bucks back if we sell that. Okay, that's about the tube. Let's see what else we have from that coherent medical laser system. Let's have another look on this black box, which comes from the same medical system. It's where all the laser beams were treated. Let's open that. I have already powered up the small helium neon laser here. You can see it's emitting light. Maybe I have to reduce my lights here. Okay, that's a nice shot. Okay, I think it works that way. So we have a small helium neon laser tube here, which has the purpose to have an aiming point for the doctor to see where exactly he is shooting the big laser. Now we have one mirror here, another mirror here, and then it goes straight to the fiber and comes out here when I move the shutter here. You can see the laser is coming out there. It's a mechanical shutter, it's just a piece of metal with a hole in it. Now the laser is blocked and now it goes through that hole into the fiber, makes a couple of loops and ends here. Now there is another wheel on this side, and this is a rotating polarizer, and its only purpose is to change the intensity of the red aiming beam. You can see it on the down here. Now it's almost gone, and now it's on full energy. Shutter here. Okay, let's have a little bit a closer look. this is how the shutter works. You can see the red dot here, the blocked laser beam that hits this black sheet metal, and when it is activated you can see it shines through that hole. That's everything. Safety shutter, or however this thing is called. Then we have another feature here. The beam passes through that hole and comes out on the other side, and here in a 45-degree angle there is a piece of glass that reflects a portion of the beam onto that board, and on that board we have some photodiodes that measure the intensity of the beam and giving feedback to the power supply to make the beam intensity stable. So you can also select a certain amount of milliwatts, and that makes sure that the output is really what you want. Now there is another feature here. This is, let me move the camera a bit. This is the second mirror. This is the first mirror from the laser tube. Laser beam goes that way. And here is a mirror in a 45-degree angle like this. It lets the red beam go through this way, and the green beam comes from underneath on that side here. This is where the big laser tube was attached, and it reflects the green beam from below into that direction, into the same axis as the aiming beam goes, into the fiber, and then to wherever you need it. There's also another feature here. I think it's a bit difficult to show that on the camera. Let me unscrew the fiber. By the way, the fiber does also have two electrical contacts here. That's the fiber. It's a tiny little hole in the middle here. Focus, you fuck. Does it help? Sometimes it helps, yes. There is the hole of the fiber and two electrical contacts here. The same contacts we have on the other side, and these contacts connect to the end fiber handpiece or whatever you have. There are different handpieces, output optics, and these optics have a resistor built in, and this resistor is connected to these 2 points. And then we have also two connections here. You see a little piece of PCB down here, makes contact to that, and the yellow cable here that comes out from that side here transmits this electrical information, this resistance value, to the electronics board, and then the electronic board or the microprocessor knows what is attached to the fiber and can display, or I don't know what it does. Maybe it regulates the power in another way, or it just knows what is attached to the other end of the fiber, which seems to be an important thing. Now there is something, maybe you can see it. there is a glass in this window here, and the glass is halfway clear and the other half has a yellow coat on it. I'm not sure if I'm able to show that in the camera. It's a little bit tricky. That's a filter you can kick in. So in this position, the greenish laser beam goes to the clear window, and if you move it in this position, you shoot it through this yellow filter, or it appears yellowish. Maybe, yes, I think you can see it now. It's a little bit difficult, and that changes the color of that laser to pure green instead of blue-green. So it filters out the blue. That's the reason why it appears yellow. These argon lasers you can have it with only one single line of greenish blue, or you can have it with multiple laser lines or laser wavelengths in one shot, and you just filter that blue part out and you get a green laser beam. The power of the green-blue laser is 2.5 watt, and the power of the green-only laser is 1 watt according to the data sheet of this machine. So we are filtering part of the laser spectrum out here to get the pure green laser. Now green is desired for all kind of surgery that has to do with blood, because blood is red and absorbs the green light very well, so it heats up and you can, for example, stop bleeding with green light. Well, I think that's about this unit. There's not much more than this.